Okay guys, so today we're going to introduce probability. The reason that we've been doing counting really is that counting is necessary for probability. As we're going to see in a moment, finding the probability of an event basically amounts to counting two things. I'm going to begin by giving some definitions that, like, don't get too hung up on this vocabulary. I'll use it occasionally, and you should at least see these words, but it's not really central to the subject, and in a way, it's kind of overly formal. It's kind of like more technical than it needs to be. But you will sometimes see these words in books and maybe on the SAT or something, so I do want to go over them. So first of all, an experiment is a repeatable action with many possible outcomes. So that could be, for example, flipping a coin, right? You can flip a coin repeatedly, and when you do that, there are different outcomes that can occur, heads or tails, right? Or you could roll a die. That's an experiment because it's a repeatable action, right? You can roll a die again and again, and each time you perform that experiment, there could be different outcomes, right? You could get a 1 or a 6 or a 5 or whatever. A sample space, the sample space of an experiment is the collection of all possible outcomes of the experiment. So if your experiment is you roll a die, then the sample space would be just the collection of all things that can happen, and that would be 1, 2, 3, 4, 5, 6. If your experiment is you flip a coin, then the sample space would be, again, the list of things that could happen, right? And that's heads or tails. Okay, another definition, event. This word I use quite a lot, event, more than these two. So an event is a subset of the sample space. Okay, so for example, you roll a die and get an even number. That's actually a subset of the sample space. The sample space for rolling a die is everything that can happen, 1, 2, 3, 4, 5, 6. But rolling a die and getting an even number is a subset. It's a sub-collection of the sample space. That's 2, 4, 6. Really, an event just means something happens, okay? Like something in particular occurs, right? So like you roll a die and you get an even number. That's an event. But you can think of an event as being a subset of the sample space, if you like. But really, an event just means something happens. Okay, so finally we're ready to define probability. The probability of an event, E, is defined as the number of elements that are in E, in the event, divided by the number of elements in the sample space. And this all kind of sounds abstract, but with an example you'll see that this corresponds to what you already know about probability. So if we look at an example, let's say you roll a die, okay, find the probability that the outcome is less than 3. Well, so the sample space, the set of all possible outcomes, is 1, 2, 3, 4, 5, 6. The event in question is you get an outcome less than 3. And that corresponds to the outcomes 1 and 2, right? So that's a subset of the sample space. Therefore, the probability of this event is given by, well, the number of elements in your event, which is 2, right? There's 2 elements here. So that's 2. Divided by the number of elements in the sample space. And of course, there are 6 elements in the sample space, so it's 2 over 6, which reduces to 1/3. Okay? I'm now going to give you an alternative definition of probability that I will pretty much always use instead of this one. They mean the same thing, but this version, I think, explains it a lot more clearly. So here's my definition of probability. The probability of an event, E, is the number of ways that the event can happen divided by the total number of possible outcomes. Okay, that really means the same thing as this, but it's phrased, I think, in a way that's more clear. So if you look at this definition, the number of ways that E can happen divided by the total number of possible outcomes, these are things that you have to count, right? If you have some event E, then to find its probability, you need to ask, or you need to count, how many ways can that event happen? That's a counting problem, and it will be your numerator. The denominator is the total number of possible outcomes. It's the number of everything that could happen in the whole universe, regardless of whether your event occurs or not. That's a separate counting problem. So really, to find the probability of an event, you just have to count 2 things. You have to count the number of ways that your event can happen, and then count the total number of things that could happen in like the whole universe and divide them. Okay, so probability mostly is just counting two things. Okay, let's do a few examples, and that'll be it. So one example, suppose you randomly rearrange the letters of the word mathy. What's the probability that your rearrangement begins with T? So let's be clear about what the event is. The event here is that the rearrangement you obtain begins with T. So, if you want to use the language from up here, the experiment is you're randomly rearranging the letters, you're scrambling them. The event is your rearrangement begins with T. Okay? So the probability that the rearrangement begins with T is going to be the number of ways that event can happen in the numerator, right? Just give me a few minutes. It's going to be the number of ways that the event can happen, right? Divided by the total number of possible outcomes, right? So we ask, how many ways can this event happen? How many ways can it happen that your rearrangement begins with T? Well, that is actually the same thing as asking how many rearrangements begin with T, right? So the probability of this occurring is going to be the number of rearrangements that begin with T, and then the denominator is going to be the total number of things that could possibly happen in the whole universe, regardless of whether your rearrangement begins with T or not. That's just the total number of rearrangements of the word, okay? So number of ways that the event can happen divided by the total number of things that could happen, regardless of whether or not your event happens. So we just have to count these things. The denominator in probability problems is usually easier to count, and I prefer to start there most of the time, so let's do that. So total number of rearrangements, regardless of whether your arrangement begins with T or not. How many rearrangements are there? Well, a good algorithm for counting the rearrangements is step 1, choose which letter goes first, right? There's 5 choices. Choose which letter comes second, it's 4 choices. 3, 2, 1, etc. So that's 5 factorial, okay? So the denominator is 5 factorial. Now the numerator, we have to count the number of rearrangements which begin with T. Well, it's a bit like you have, 5 blank spaces. And the last space is already filled in with T. No, sorry, the beginning space is filled in with T, right? You have no choice about that. There's nothing to decide with regard to this T. It's just there. All you have to decide is what to put in the remaining blank spaces. You have 4 choices for this one, 3 choices for this one, 2 for that one. So that's 4 factorial in the numerator. So 4 factorial over 5 factorial, that reduces to 1/5. Okay? Here's another example. Suppose there are 10 students and one of them is Nika. If you randomly select 3 people to form a team, what's the probability that Nika is on the team? So the event here is Nika's on the team. So the probability that occurs is the number of ways that this can happen divided by the total number of things that can happen. In other words, the numerator, the number of ways that this event can happen, that's just the number of teams with Nika. It's the number of teams that have Nika on it. And then the denominator is, the total number of things that could possibly happen. That's just the total number of possible teams that you could construct, regardless of whether or not Nika's on the team. All right, so we have to count those 2 things. The denominator is usually easier, so total number of possible teams that you could make, regardless of whether Nika's on there or not. Well, there's 10 students, 3 people. Team is like the prototypical unordered collection. You use a choose number for that, right? Like there's no first person on the team, second person on the team. So 10 choose 3, right? That's the number of 3-person teams you can make from 10 people. Now the numerator, the number of teams with Nika, what's an algorithm for generating that? If you want to construct a team that has Nika on it, what do you really have to do? Well, Nika's already on the team. There's nothing to decide about that. You don't have to make any decisions about that. Nika's on the team. All you really have to decide to construct a team with Nika on it is to choose the other 2 people on the team. Now, of course, those other 2 people aren't Nika because Nika is already on the team. So you have to choose 2 people who aren't Nika to complete the team. And there are 9 of those people. So 9 choose 2. That's the number of teams that have Nika on it. And if you actually simplify this, it's just some decimal between 0 and 1, but I'm not really that interested in simplifying the numbers. Okay. Yeah, I think there's one more example on the worksheet that you can take a look at and read if you want, but I think this is a pretty good explanation for now. Okay.